The strong law of large numbers, which we have now completely proved, is a landmark result in probability theory. One of the reasons is that it justifies the entire frequentist philosophy of probability and statistics, and is therefore the basis of all scientific experimentation. The frequentist perspective is that probability is fundamentally about frequency. That is, the probability of an event, its likelihood, simply means how often that event occurs under many, many repeated trials. In our language, given an event A in our probability space, what does the probability of A mean? Using the strong law of large numbers, we can construe it as follows. Let's do repeated independent trials of an experiment that tests whether A occurs or not. In each trial, we record a 1 if the event A occurs during that experimental trial, and we record a 0 if A does not occur. And then we average the results. We average all of those 1s and 0s after many, many trials. Why does that tell us something about the probability here? Well, if I let xn be the random variable that I recorded there, a 0, 1 valued random variable, then it's supposed to have the same distribution as the indicator function of the event A. Now, as I conduct different trials, the results of one trial should not affect the results of any of the other trials. The trials are independent, and so these random variables are independent. They are 0, 1 valued random variables which are bounded and therefore L1, and therefore by the strong law of large numbers, we get that the empirical average of those random variables converges almost surely to the expected value of any one of them, which has the same distribution as the indicator of A, and the expected value of the indicator of A is the probability of the event A. And there we have it. The strong law of large numbers tells us that empirical averages in repeated trials of experiments tell us probabilities of events. That's fine and dandy, but this is not a philosophy class. I'd like to highlight now some applications of the strong law of large numbers to actual probability problems, and we'll see many more in the coming weeks and months. The basic efficacy of the strong law of large numbers is its universal nature. It does not depend at all on the underlying distribution of the random variables. It only depends on their expected value. And so it can be a very useful tool in cases where we have limited information about the distribution of the random variables we're interested in. So that brings us to the classic question, how many probabilists does it take to change a light bulb? Well, this is not a joke. We're going to talk about renewal theory. Let xn be a sequence of IID L1 random variables that are non-negative and are not almost surely 0. So there is a positive probability that they are positive. What does that have to do with light bulbs? Well, we're using xn in this case to model the lifetime of a light bulb. It's going to burn out at some finite time, strictly positive hopefully, at which point we're going to replace it with a new one. We'll take the new one out of the same package that the old one came from. They were produced in the same factory, went through the same shipping, and so we expect that they should have the same conditions for when they burn out. But of course, when they actually burn out is a random event. So what that means is that the lifetime of the light bulb, while random, is identically distributed between the different light bulbs. Similarly, when the 7th light bulb you've installed burns out, should not have any effect on how long the 8th light bulb lasts, or how long the 3rd light bulb lasted. So those lifetime random variables are independent. The question we're going to be interested in here is not how many probabilists it takes to change these light bulbs, but how many light bulbs we need over a given period of time. To get at that, let's look at the sum of those lifetime variables. That is equal to the length of time from when we turn on the first light bulb until the nth light bulb we've installed in succession burns out. We're making the assumption here that when a light bulb burns out, we instantly replace it with a new one. The question is, if we'd like to stock up with light bulbs for the next year, how many ought we buy? So that is answered by this number, nt, where t is 1 year in that example, the number of light bulbs that will be used up over a time period t, and that's just going to be the supremum over all natural numbers n, for which that sum, Sn, is less than or equal to t. This is a random integer that is determined by the distribution of the light bulb variables. So if we knew that distribution, we could say exactly what the distribution of nt is. It's going to depend on the distribution of Sn, of course, here, and the distribution of Sn is the distribution of a sum of independent random variables, and so it's the convolution of their individual distributions. They're all identically distributed, and so this is the distribution of any one of them, n-fold convolution power. So that distribution convolved with itself n times. It's also going to depend on t. And if we knew what this distribution was, we could write down a kind of formula for the distribution of this random variable. But that's not really going to help us answer this question, because we don't know what this distribution is. We can't predict, without careful analysis of the light bulb manufacturing process and the shipping process and any vibrations that might have happened and the conditions in the house and so on, what the distribution of that random variable is. Nor would we want to try. Instead, what we might be able to ascertain, using the strong law of large numbers, is what is the expected value of these random variables. Well, that's just going to be the limit of this divided by n. So if we do this over a long enough period of time and calculate Sn over n for large n, we'll have an estimate from the strong law of large numbers for what the average, the expected value of these random variables is. And by the way, that's exactly what's marked on the box, except it's given in terms of half-life, which means they're assuming that these random variables xn have an exponential distribution. We're not going to make that assumption in this example. We're going to see that, at least for large t, answering the question of how does nt behave can be accomplished without any knowledge of the distribution of the xn's, other than the expected value. So to see what kind of answer we might expect to get, let's do a back-of-the-envelope calculation. Suppose that the xn's aren't actually random, or they're not very random. All of the light bulbs actually last for 10,000 hours plus or minus 5 hours, and so we'll just ignore that little bit of random noise. So in that case, what we're saying is that xn and xm are pretty close to equal for all n and m, which means that the sum of the first n of them is pretty close to n times the first one. And that would mean that this variable nt is the supremum over all n, for which n times x1 is less than or equal to t, which is of course going to be t over x1. Although that's not necessarily an integer, so it's probably the ceiling of that, but we're making rough approximations here anyway. So what that says is that in this back-of-the-envelope calculation, we would expect that for large t anyway, nt over t would behave like 1 over x for any one of those variables. Now that would say that nt over t is random for all t without any concentration. But that's an invalid conclusion because we assumed that the xn's were basically non-random to get here. If the xn's are basically non-random, that means that x1 is basically equal to the expected value of x1. And what actually holds true is that nt over t converges to 1 over the expected value of x1. So for that to make any sense, we better make sure that x1 has a strictly positive expected value. Well, that just follows from the assumptions. The x1s were all non-negative, which means they have non-negative expected value, but we also assumed that they have positive probability of being strictly positive, whereas if the expected value of a non-negative random variable is 0, that means that its L1 norm is 0, which means that it's equal to 0 almost surely, and that contradicts that assumption. So we can indeed divide by this strictly positive number. Now there are a few other things that we can tell about these random variables from the assumptions. First, we assumed that the xn's are in L1, and that means that they are almost surely finite. It follows from there that the sum of any finite number of them, Sn, is almost surely finite. So that is, if we let omega 1 be the event that all of the xn's are finite, then that is a full probability event. The reason is that it is a countable intersection of measure 1 sets, and therefore has probability 1. Now, one nice feature of working on the set omega 1 is that on that set, the random integer nt diverges to infinity as t goes to infinity. That's true because otherwise, we would have that nt is always less than or equal to some upper bound n naught. But that would mean that the largest integer for which Sn is less than or equal to t is always less than or equal to n naught, which means that at time n naught plus 1, Sn must equal infinity. But that doesn't happen on the event in question. So nt does go off to infinity, and in fact from the definition we can see that nt is a non-decreasing function of t. So nt increases to infinity. Now, by the strong law of large numbers, the empirical average, Sn over n, converges almost surely to the expected value of x1, and so the event that that convergence happens is another probability 1 event. For the rest of this problem, we're going to work on the intersection of these two probability 1 events, which is, therefore, a probability 1 event. Ergo, the strong law of large numbers holds everywhere, and nt increases to infinity surely. Now we're interested in what happens to nt over t for large t. To get at that, we look at the definition of nt. Nt is the largest integer for which Snt is less than or equal to t. In other words, it's uniquely determined by this pair of inequalities. S of nt is less than or equal to t, but S of nt plus 1 is greater than t. Now, since nt goes off to infinity, I can, at least for sufficiently large t, divide all sides of this by the strictly positive nt. And now all I have to note is that if I take Snt divided by nt, well, just to be very careful, let's note that this is still random, and the randomness is coming from two sources. So in each outcome, we're evaluating s of omega at the random integer nt of omega and dividing by the random integer nt of omega. That might look a little daunting, but we can still take the limit as t goes to infinity, because we know that surely on the event we're working on, nt of omega for every omega goes to infinity as t goes to infinity. And therefore, by the strong law of large numbers, this ratio goes to the expected value of x1. Now, from the inequality that we have up here, this is less than or equal to the limit, if it exists, or even if it is not, the lim inf, as n goes to infinity, of t over nt. Very similarly, if we look at the lim sup as t goes to infinity of t over nt, that will, by this inequality, be less than or equal to the lim sup as t goes to infinity of snt plus 1 divided by nt. Now, we would like to compare that to something that the strong law of large numbers applies to, which means we have to divide sk by k. And here we're dividing sk plus 1 by k. So what do? We multiply by k plus 1 over k plus 1. And now we group these like this. And by the same argument we gave over here, snt plus 1 over nt plus 1 tends to the expected value of x1. So we just have to look at the limit of nt plus 1 divided by nt. But that's 1 plus 1 over nt, and we know that nt goes to infinity, and so that converges to 1. And therefore, this lim sup is the limit which, by the strong law of large numbers, is the expected value of x1. And so, utilizing this pair of inequalities, we see that the lim inf of this ratio is greater than that, and its lim sup is less than or equal to that, which means that the lim and the lim sup are both equal to that. And we have concluded that the limit as t goes to infinity of t over nt is, on this probability 1 event, the expected value of x1, which is strictly positive, and therefore, by limit theorems, we take the ratio and get the result that we wanted, which is that nt over t almost surely converges to 1 over the expected value of x1. This shouldn't be a surprise. If we expect a light bulb to last on average for 1 month, then over the course of 1 year, we're going to need 1 over 1 month times the year light bulbs. That is, 12 light bulbs. None of these results will be surprising. The important thing is that we can prove them rigorously without back-of-the-envelope, very hand-wavy calculations. Now, that was not a very realistic example. Why? Because I have a burned-out light bulb right over there, and I haven't changed it in about a month and a half. We can't expect the light bulbs to be replaced the instant that they burn out. So a more realistic model would be to have 2 sequences of random variables. Xn are IID random variables that represent the length of time that each light bulb lasts, and Yn are IID random variables that represent the length of time after the nth light bulb burns out before the n plus first is put in its place. It's natural to assume that these are IID. Again, they all came from the same batch. And we'll also assume that these waiting times in between replacements are IID, meaning that I'm the guy that replaced them every time and I'm equally lazy over all periods of time. And we'll make the same assumptions that none of these random variables is almost surely 0. If these were almost surely 0, then we're just back in the old example. There's no reason, however, to think that these ones and these ones are all identically distributed. The distribution of these comes from the design of the light bulb and how they were stored and so forth. The distribution of these comes from my character. So these are 2 separate sequences of IID random variables that are not identically distributed between them. We will, however, assume that the x's and the y's are independent from each other. That is to say, the length of time that it takes for the last light bulb to burn out will not affect how long it takes me to replace it. That's probably not a realistic assumption, because if the light bulb burns out 2 minutes after I replace it, I'm probably going to go grab the next one right away. Nevertheless, we're going to make that assumption here in order to do a calculation. Now, we can sort of apply the last example right away to say a few things. The time until the n plus first light bulb is replaced is this sum here. The first light bulb burns out and then is replaced. The second light bulb burns out and then is replaced. The nth light bulb burns out and then is replaced. So the n plus first light bulb switches on. So let's call that Sn now. And now these are our new IID random variables. So if we let nt be the number of light bulbs needed through time t like before, now that's going to be this. The largest n for which this sum is less than or equal to t. And following exactly the previous example, because we have all the same conditions met, we know that nt over t is going to converge as t goes to infinity to 1 over the expected value of each term in the sum, which is 1 over the sum of the 2 expected values. Okay, but the question I want to answer this time is, what fraction of the time is there light in the room? We can write out a formula for what that fraction of time is in terms of these random variables. We'll do that in a moment. But let's just start by doing our back-of-the-envelope calculation to see how it should behave, again, for large t. If our x's, the time the light bulbs last, are not very random, they all last pretty much the same amount of time, then the sum of the first n of them should be approximately equal to n times x1. And the total time until that n plus first burns out is going to be approximately n times x1 plus n times y1. Again, here assuming for the sake of this back-of-the-envelope calculation that there isn't much randomness in the length of time it takes me to replace each light bulb after it burns out. And so that would say that the fraction of time between when we start and when the n plus first light bulb is replaced, that there is light in the room, is going to be about x1 over x1 plus y1. So what's the actual result going to be? It's going to be that for large t, the ratio is the expected value of x1 divided by the expected value of x1 plus y1. In order to prove that, we're going to need a lemma, which we might have proved on the way to the strong law of large numbers, but didn't end up needing, but is useful and interesting in its own right. If x is an L1 random variable, and xn is a sequence of identically distributed, not necessarily independent, random variables all with the same distribution as x, then xn over n converges to 0 almost surely. Okay. Why is that true? Well, it follows pretty quickly from this fact, which we did prove en route to the strong law of large numbers, this strong generalization of Markov's inequality, that for any fixed random variable, the sum of the probabilities that absolute value of x is bigger than or equal to n times epsilon over all positive integers n is less than or equal to 1 over epsilon times the L1 norm of x for any epsilon greater than 0. So that means that in our situation here, if I look at the probability that xn is bigger than or equal to n times epsilon, because of the identical distribution, that's the probability that x1, or x, is bigger than or equal to n times epsilon, which is bounded by this over that whole sum. But this is the probability that xn over n is bigger than or equal to epsilon. So here I have a sequence of events that xn over n is bigger than epsilon in absolute value, and the probabilities of those events are summable because x is an L1 random variable. And therefore, by the first Borel-Cantelli lemma, the event that xn over n is bigger than or equal to epsilon for infinitely many n has probability 0. So if we let omega epsilon be the event that xn over n in absolute value is strictly less than epsilon eventually for all large n, which is the complement of this event, that has probability 1 for each epsilon. Now that's almost what we need here, because this is precisely to say that xn over n converges to 0, provided that you make that statement for all epsilon inside. But right now, we have it for all epsilon outside. And the set of all epsilons here is uncountable, so we can't just take the intersection of all of them and expect that the probability to stay 1. But that's okay, because we can characterize limits instead of being for all epsilon, we can make it for all 1 over k for large k, and that is a countable set. So the event that the limit of xn over n is 0 is exactly the same as the event that for all natural numbers k bigger than or equal to 1, xn over n is less than 1 over k for all large n. And using the notation from the previous line, that is nothing other than the intersection over all integers k of omega 1 over k. The sets omega 1 over k all have probability 1, and therefore the probability of this countable intersection of them has probability 1, which proves the lemma. Okay, now back to the realistic light bulb problem. So we showed, thanks to the first example, that nt, the number of light bulbs needed up to time t, converges when divided by t to 1 over the expected value of x1 plus the expected value of y1. Now what we're interested in is the fraction of time there's light in the room, so let's let t be the length of time in the interval from 0 up to t that there is a working light bulb installed. So we can write down a formula exactly for this. It's pretty close to the sum n going from 1 up to nt of xn. So that's the sum of all of the times that the light bulbs were installed until the nth one burned out. However, it could happen that the n plus first is installed before time t and doesn't burn out before time t, which means that last bit of the last term isn't included in this sum. So we can adjust that by saying that the actual time is equal to xnt plus 1 minimized with the total length of time minus the sum of the x's and the y's up to time t. So there's a formula for the time in question, and now what we want to do is divide that by t and see what happens to it. Well, I don't really want to deal with this term. Looks complicated. And we don't need to deal with that term in the limit, thanks to the previous lemma. If we set tt tilde to just be that first term, which we expect to dominate this sum, then we see that since this term here is positive, tt is bounded below by tt tilde, but also it's bounded above by that term, because the term we're adding on is this or this, whichever is smaller. And so it's in between tt tilde and tt tilde plus x nt plus 1. And now this is looking a lot like what we had last time. We're going to divide by t on all sides. And now we note that by the lemma that we just proved, x nt plus 1 divided by t, which can be written as x nt plus 1 divided by nt plus 1 times nt plus 1 over t, is going to go to 0. Because nt plus 1 over t converges to a finite number, 1 over the expected value of x1 plus y1. And since nt goes to infinity, we know from the lemma that x nt plus 1 over nt plus 1 goes to 0, almost surely. And so as t grows, we can ignore this term, and we get that the limit of tt over t is the same as the limit of t tilde t over t. So that's all we need to calculate now is this limit. Well, that's the limit as t goes to infinity of 1 over t times the sum of the xn's up to this random time nt. And we will do exactly the same thing again, multiplying and dividing by nt over nt to write this as the limit of nt over t times what we would have called snt over nt in the last example, but in this case let's just make it clear by writing it as the sum n going from 1 up to nt of xn divided by nt. We know from earlier in this proof that nt over t converges to 1 over the expected value of x1 plus the expected value of y1. And we know from the strong law of large numbers that this converges to the expected value of x1. Again, even though we are evaluating the sum at a random time, we proved that almost surely, on the event that we're working on, surely nt tends to infinity as t goes to infinity. And so as t goes to infinity, this is just the empirical average, and it converges to the expected value. And that concludes the proof of the result that we wanted. So there is a brief introduction to renewal theory. We could add more realistic assumptions and get out more complicated looking answers. And we will see lots of applications in other arenas of the strong law of large numbers as we go forward. But that's not the direction we're going to go next. Our next direction in this course is to understand how much randomness is left in the empirical average, Sn over n. We know that it converges to a constant, almost surely. And we know that provided the random variables in question are, say, L2, that convergence is at rate about 1 over root n. So what happens when we blow up by the square root of n? We have this result we'll see later, the law of the iterated logarithm, that says something very precise about the lim sup. But what about the distribution? Sn over n is getting very concentrated about the mean. If we then blow up by the exact rate of concentration, what happens to the distribution of what's left? What is the random profile of the fluctuations about the mean? Stay tuned.